Hello students, my name is Shashank Shekhar and we started the chapter Chemical Kinetics and today is the third lecture of this series. Right. So if we see the syllabus, so we have covered this part. The rate of a reaction. What is the rate of reaction? We have seen this thing. And what are the factors that would affect this rate of reactions? We have just seen an introduction to these factors. We will see the detail in the upcoming lectures. So today I will be mainly dealing with this concentration term. So what does concentration have the effect on this rate of reaction? So that is mainly decided by the order of the reaction, that in what order a reactant is affecting a reaction rate. So we will see it what it is. So for today's class I will just give you what is order, how to determine it, and what are the steps taken that would be discussed in the next lecture. Okay, so if you see the topics that are to be covered today, so the first of all, the topic would be the effect of reactant concentration. So basically, this rate law is associated with reactant concentration. This is the rate law. So study rate law, and then we'll see a illustration of it, that how can we apply it, say apply it on a reaction so that we can get our rate law. But then we will give you what is order of reaction. Then something which is called rate constant. We will discuss about this unit. It is asked in the exam sometimes. And then we will try to generalize the unit of rate constant. So these are today's topic. The first topic is effect of reactant concentration. So here you are seeing a table, right? Here you are seeing a table, and the reaction goes like this. Sorry for not mentioning the reaction, but just assume that this is the reactant and this is also a reactant. So this both are acting as a reactant here. Here we have time t1 and here we have time t2. So we are going from 0 to 50, then 50 to 100, 100 to 150, and 150 to 200. And this is the average rate of reaction, that is multiplied by 10 to the power 4 mole per liter per second. If you don't understand the meaning of this, it is very simple. Understand it in this way, that this value is the average rate of reaction multiplied by 10 to the power 4. So if you want to find the R average, so it is given that this value is equals to 10 to the power 4. Okay, so this value is equals to rate average into 10 to the power 4. So that would give the value of rate average is equals to 1.90 in 10 to the power minus 4. So this is the meaning of this. Why is it not written in this form? Because it would be hazy to look at it. So that to make it more clearer, we have used this, say, generalization, right? So if you look at this table here, you can see that rate generally increase when the concentration increase, reactant concentration increase. So this is a direct, you can say, analogy from this equilibrium Le Chatterjee principle, that if we increase the concentration of reactant, we will get the rate of reaction also increased. Okay, why? Because now the reaction will try to submerge, or you can say nullify that reactant increase, and to do so it will consume more and more reactant, and that also fastly. So we can say that a rate of reaction depends upon the concentration. So if I want to just define it, or you can say mean to quantify it using a law, so that would be, so if we just equate the rate of reaction with the concentration with some power, that would be called as rate law. So something rate law. This is the most important part of this lecture, that is rate law. Okay. Now it is also noted rate equation or rate expression. So this rate law is also termed as rate equation or rate expression. Now how this concentration of reactant is affecting the reaction rate, you can see very clearly in this table right here that is given. So if you see that we have initially 0.1 m mole per liter concentration of this C4H9Cl, at time t1, and when we see at time t2, its concentration decreases to 0.0905, and the time that has been taken is equals to 50. 0 to 50, that is 50 minus 0 would be 50. So if you want to calculate the rate constant, that would be final concentration minus initial concentration, that is C4H9 concentration at time t2, minus C4H9Cl concentration as t1, divided by the time, that is t2 minus t1, and it is put again with a negative sign. So you have seen this formula, that is R average is equals to change in concentration of R reactant divided by change in concentration of time, sorry, change in time, right? Again with a negative sign here. Let me put it here for you. Here. So this formula you have seen. So if I want to put all these values, that would give us, so if I write it here, suppose I am writing it here. R average would give given by 0.0905. 0.0 negative sign is here. 0.0905 minus 0.100 divided by 50. So if you just solve it, so you will get here 0.10, that means 10 minus 5, and here we will get it as 0, that is 9 minus 0 would give us 0. Again 9 minus 9 would give us 0, and it would be 0, right? This. Okay. So this would give you this. Right. So this is the value. Now if you divide by 50, so let me do it for you. It is 0.10, 0.0905. Here it is 0 minus. It will be 5, 9 minus 0, 0. Sorry, 9 minus 0, 9. 9 again, 9 minus 9, 0. 1.0. So this is the value we got. Okay. And that is divided by 50. So if you just solve it, you will get 5 1 5, 5 9 45. It is 1.90. 1.90 into 10 to the power minus 4. So it is simply calculated in this way. No rocket science. You just have to subtract the final concentration with the initial concentration with a negative sign. So that would give you overall positive sign of the rate of reaction, average rate of reaction. So the same thing is written here. Okay. We got here 1.90 multiplied by 10 to the power 4. So this value would give you this. Similarly, if you do take the another time instant, that is going from 50 to 100, then again you will subtract this 0.0820 minus 0.0905 divided by 50, or you can say 100 minus 50. Again you would get this 1.70. So you can see here one more thing, that the product concentration is slowly decreasing. Decreasing how? We are going from 0.1 to 0.905, then 0.905 to 0.0820, then 0.074. So we are decreasing the concentration of reactant one by one. At the same time, you can see that the rate of reaction is also decreasing. 1.90, then we have 1.70, 1.58, 1.40, 1.22, and at last it goes on decreasing. So we can see here that as the concentration of reactant is decreasing down this table, the average rate of reaction, or say simply take the rate of reaction, it can be average or instantaneous, both will decrease. It does not matter we are taking average or instantaneous. Both will decrease as we move further in the reaction, or we can say decrease the reactant concentration due to conversion into its product. So as we are transversing to time, this concentration is decreasing of the reactant concentration is decreasing, and with time and due to decrease in concentration of reactant, the rate of reaction is also decreasing. So this is the effect of reactant concentration. Now this effect is something we can say it is not quantized in a way. So to quantize that, because this is quite abruptly looking, this change is looking quite abruptly. Okay, so to quantify it, we have introduced the term rate law. So what is this rate law implicating? If you see here, the very definition of rate law says that it is the expression in which the reaction rate is given, means the reaction rate can be written in the form of what? Molar concentration of reactants only, not products. Remember this thing, rate law can never be written in terms of product. It always be written in terms of reactant. Okay. So what we are saying is that the rate law is the expression in which the molar concentration of reactant can be used to express the rate of reaction. And this molar concentration of reactant is raised to some power. Now, what is this power? I would discuss this later, but it can be or cannot be equal to its stoichiometric coefficient. So that case also we will discuss. So when it will be equal to stoichiometric coefficient, or when it will not be equal to its stoichiometric coefficient. So for this, I have put up illustration here. Suppose we have a reaction, which in which we are going from reactant AB to CD, and this A, B, C, this small A, B, C, D are the stoichiometric coefficient of this reactants or product. So is this clear to you? So basically, what are we dealing with? We are dealing with a hypothetical reaction that has reactant A and B and has the product C and D, and the stoichiometric coefficient are small a, capital B, small c, and capital D. Okay, so this has a stoichiometric coefficient. Do not get confused with it. Okay, so this is clear. Now, according to this statement, that what is rate law? It is the expression in which the reaction rate. The reaction rate, we have written rate, is directly proportional to this molar concentration of reactant. So what are the reactants here? So if you see here, with the help of chemical equation, you can easily predict that the reactants are A and B. So this we have taken the molar concentration of A and B by representing it with inside a square bracket. So rate is directly proportional to concentration of A raised to the power x. So it is written, it is also written here that they can be raised to the power some power, and that may or may not be equal to a stoichiometric coefficient. So it is saying that this x can or cannot be equal to this A. It will depend on the reaction complexity. So that is a different matter to discuss. Or it cannot be equal also. So both can be possible. So it is completely you can say experimental. Then we have the another reactant B. So if you want to write the complete rate law, all of the reactants should be considered. And now their power may be decided on the basis of this rate law, sorry, experimental data. Okay, so this is our rate expression for this reaction. Now what we can do, we can simply can say simplify it, right? We can simplify it later on. How? What we have done, we have used this term minus dr by dt. So do not get panic with it. It is very easy to understand what it is written. It is our very initial definition of rate constant, sorry, rate of reaction, in which we expressed it in the terms of change in concentration of reactant and product. So we have taken the change in concentration of reactant by the time taken proceeded with preceded with a negative sign. So this is the rate of reaction. Also, we have removed this proportionality constant and introduced rate constant. So this is called as rate constant. Okay. So the rate of reaction is equals to the rate constant multiplied by A raised to the power x b raised to the power y. Both are a reactant here, and this k is called as the rate constant. So we have introduced a negative sign. So remember this. So this will confuse you always why it is written negative sign, and student do mistake in the exam by not introducing the negative sign. Okay, so this was our rate law. Now let us see illustration to get it more clear. So look at this, say our illustration that we have here. So we have taken a reaction. This is the reaction that we have, in which we are say reacting this nitrogen oxide with oxygen, and it is given a higher oxidation state of nitrogen. So consider this reaction. So what we see here, that we have an experimental data. Okay, so we have done experiment and got some result. So in this experiment, we have taken different concentration of NO and O2. Means both the reactants are taken in different concentration. And then we have seen what is the initial rate of formation of NO2. So this rate law, this rate of reaction here is basically the instantaneous rate of reaction. So this is the instantaneous rate of reaction, not the average rate of reaction. And in the coming lectures, I would say all of these rate of reaction would be instantaneous only, because that is of more importance. Okay, that is of more importance. So what are we doing here? We are taking different concentration of NO and O2. We are taking different combinations of both of the concentration, and then we are, say, measuring the instantaneous rate of reaction, or simply the rate of reaction, or rate of formation, you would say, of NO2, rate of formation of NO2, and seeing what is the effect of this initial concentration change on the rate of reaction. So first of all, if you see this, you can see that we have initially taken 0.30 molar concentration of this NO and 0.30 molar concentration of this oxygen. So due to this, we got the initial rate as 0.096. Now what we have done, we have kept this oxygen concentration constant. Okay, it is kept constant, and we have doubled this NO concentration. What we have done, we have kept oxygen concentration constant and changed the concentration of this NO, and simply I could say that I have doubled it from 0.30 to 0.60, means multiplied by 2. Now what is the effect on this rate of reaction of this doubling of reactant concentration? You can see that the reaction rate of reaction is been 4 times now. So it is 0.096 multiplied by 4. So if you multiply it, it would give you 4 6 are 24, 2 carry, 4 9 36, 37 38. Again 3 carry, we have 0. So we got 0 again, and 400. So you can see that we have a change of multiplied by 4 if we just increase to it double. If we just double it, we can see that the rate of reaction is increased four times, by increased a factor of 4 times. So what does this indicate? So this indicate that the rate depends on the square of the concentration, or we can say that the this if we can say that if we double the rate of reaction, we are getting 4 times. Sorry, if we are doubling the concentration of the reactant, we are getting the rate of reaction 4 times. Okay, so that would mean that the concentration is somewhat square times dependent on the concentration of this NO, or the rate of reaction is square time dependent on the concentration of NO. Now next what we have done, we have kept this thing same. So this is same. Now we have doubled this concentration. We have doubled this concentration. So that results in also doubling of this rate of reaction. So if we are just doubling this oxygen concentration by 2, or multiplying it by 2, then this rate of reaction is also getting multiplied by 2. Is also getting multiplied by 2. So that would mean the rate depends on the concentration of O2 to the first power. So what do I want to say here is that if we are doubling the rate of reaction, if we are doubling the NO concentration by 2, we are getting the rate of reaction 4 times, increased by factor of 4 times. And if we are doubling the concentration of this O2, we are just doubling the rate of reaction. That means that NO concentration is kind of square times, doing the square times the same. So it is this rate of reaction is dependent on the square of the concentration of NO. Similarly, this O2 is raised to the power 1, means the rate of reaction depends on concentration of O2 raised to the power 1. So overall, if you want, now we can write that the rate of this reaction can be written as rate constant multiplied by NO2 concentration. Sorry, it is a brace bracket here. Okay, so it has a power 2 and it has a power 1. Now, if you look at this chemical equation, you can see that here also the stoichiometric coefficient of this NO is 2 and this oxygen is 1. So you can say that this stoichiometric coefficient is equal to its power, but this is not final. Now I will give you some examples where you will see that okay, we have this different stoichiometric coefficient, but the outcome of this rate constant is different. Okay, so let us see some examples here. So the first is the reaction of chloroform with chlorine to give this carbon tetrachloride and HCl. So for this, experimental data says that the rate looks like this: 1 by 2 raised to the power 1 by 2, and it is raised to the power 1. Okay, so this is good. We have the power 1. But if you look here, that means Cl2 has the power of 1 by 2, but the coefficient here is 1. It is not 1 by 2. So that would suggest that in this case, this stoichiometric coefficient is not equal to this power. Again, next one, we have this CH3COC2H5, means acetic ester, you can say, and it is reacting with water to give us acetic acid and ethanol. This is ethyl methyl ether. Okay, ethyl methyl ester. I think it is ester, na? Ester. It is ester. Yeah. So this is ethanoic methane, something like that. So we will not go to the nomenclature right now. Okay. So that if you consider the rate law, if the experimentally it is found that it is in this way, means with respect to this CH3CO C2H5, it has the power 1, but with respect to H2O, it has a power 0. Means it is independent of the concentration of H2O. Whatever we take the concentration of H2O, we would see no change in the rate. So that is quite an interesting outcome. Why? Because of two things. First of all, you can see the stoichiometric coefficient of H2O is not 0. It's not possible also. So in this case, we can say that the power is not equal to stoichiometric coefficient. What is the second thing? The second thing you have seen that okay, it can have the power of 0 also, means the rate of reaction can be independent of the concentration of the reactant. Okay, so very interesting thing. Just think of it that something is taking part in a reaction and still, and not being a catalyst also, still it has a kind of zero independency on this rate of reaction, or the rate of reaction is independent of this H2O concentration. So in this reaction, the exponent of the concentration term are not same as the stoichiometric coefficient. Okay, so this is clear. So in this case, the concentration terms are not raised to the power which is equals to a stoichiometric coefficient. So do not get excited and just keep the power that is the concentration of this coefficient. There are some cases, we will discuss it later, but in some cases it will be equal, in some cases it would not be equal. Now what is the rate law? Now the rate law cannot be predicted by merely looking at the balanced chemical equation. So very important line to look upon. So since I have told that this can or cannot be equal to stoichiometric coefficient, so you cannot just write the rate law just while looking at this rate equation. This rate equation or this rate equation, you cannot just simply predict it by looking at the rate equation. there have to be done something experimentally. You have to take some data, plot it, or you can say plot it with a plotted, or put it in a pen or paper and try to just solve it to get the rate law, accurate rate law. Okay, so these are the two illustrations which says that the rate law uh, is the expression which relates, or you can say in which we say that the rate of reaction is directly proportional to the rate of concentration of the reactant raised to some power that can be or cannot be equal to its stoichiometric coefficient. So this is the final rate law. And what are the examples in which we have different power, means different stoichiometric coefficient and different power? The first one and the second one shows is very clear. And in some cases, like the previous one, in which we are reacting NO with O2, we have seen that okay, the stoichiometric coefficient and the rate law of power are both same. Okay, so this is clear, right? Now, what is this order of reaction? Very can say very important point of this rate of equation. So you must be saying that okay, all of these are important. I would say that rate law is the important, and to understand rate law, the order of reaction, to understand order of reaction is very important. So this is the thing. Now, if you see the rate equation for two different products, say A and B, then we can write that rate is equals to K, two different reactant A and B. So for this, we can write as rate is equals to K A to the power X, B to the power Y. What is this X and Y? This represent how sensitive the rate is to change in concentration. You have seen this thing that if you just do a square of it, it gives 4 times. So you are kind of checking the sensitivity. So what do we mean here? That X and Y indicate that how sensitive is the ratio. The ratio is to the change in concentration of A and B. This is clear. Now the sum of this power. What are the powers? The power here are X and Y. The sum of this power, that is X plus Y, is giving the overall order of reaction. What is this X and Y giving? It is giving the overall order of reaction. Where X and Y, what do they represent individually? So this is the overall order of the reaction. If you talk about the individual rate of reaction, so X is the order of reaction with respect to A, and Y is the order of reaction with respect to B. The same thing is written here. The sum of the power of concentration reacted in the rate law expression is called the order of that chemical reaction. Now, order can be 0, 1, 2, 3, and even a fraction. Okay. A zero order reaction means that the rate of equation is independent of the concentration of reactant. So that's a different thing. We have seen it right now also. But first of all, the order of reaction can be 0, 1, 2, 3, and even fraction, but it cannot be negative. It can never ever be negative. It can be 0, it can be 1, it can be 2, it can be fractional like 3 by 2, 4 by 2, anything, but it cannot be less than 0. Now, what is this zero order reaction means? Suppose we take our first value, is 0. So that would represent that the reaction is independent of the concentration of reactant. What does it indicate? That what it does not matter whatever we take this concentration of this reactant, we will get the reaction rate same. So this kind of reactant, we can say, does not affect the rate of reaction in any way, and it is zero order with respect to that reactant. So this is the order of reaction. Next is the unit of rate constant. So this is very important. Okay, this is very important. Keeping in mind the short questions that we get. So very easy to solve, easy to get the answer. So how can we decide the rate law first of all? So we can decide the rate law if we look properly at this rate. Sorry, we can define get the unit of this rate constant if we look at this rate law minutely. Very easy to predict. So for zero order reaction, suppose the reaction is having zero order. What would we write? That rate is equals to minus dA by dt is equals to K0. And since the power is 0 with respect to reactant, we get it only K0. So what would be the unit of K0? It would be unit of A divided by unit of T. Okay, this is clear. So what I am saying that unit of k is equals to unit of a by unit of t. What is this unit of a? So it is having a inside the square bracket that would give us mole per decimeter cube. So do not get confused with it. It is liter only. That is written in a different form. Okay. Divided by unit of time. That is second. So that would give us mole per decimeter cube per second. How? We have the mole per decimeter cube, and again we introduce second that goes up and gives up our s to the power minus 1. So this is for zero order reaction. Okay. Now next is this rate of reaction for first order. For first order. So with first order we can introduce a reactant concentration A. Suppose A is the reactant. Then we raise it to the power 1. That would give us this. Now what is this K1 equals to? It is equals to minus 1 by A. We have a negative sign here. The A goes here. Minus 1 by A multiplied by dA by dt. Now, what is this A representing? It is concentration of A. That is mole per decimeter cube. Again, concentration of A divided by time concentration. Sorry, unit of time. Unit of time. So it is concentration of A. This is also concentration of A unit, and this is unit of time. So we have mole per decimeter cube. Mole per decimeter cube. So this both get cancelled out, and we are only left with per second. That is the unit of this time is per second. So this is our unit of K for first order reaction. Then we have second order reaction. We have taken two cases. First, in which both the reactants are same, and second, in which both the reactants are different. So first, let us consider if both the reactants are same. So what will happen? So in this case, we can write that the rate is equals to minus A raised to the power A. So this is not A, sorry, this D minus dA by dt. It is a differential form. Then K2 multiplied by A to the power 2. Why it is 2? Because it is now a second order reaction. So it will have a power of 2. Again, next we have just put upon here K2 is equals to minus 1 by A square into dA by dt. Now what is the unit of this A square? It would be mole per decimeter cube raised to the power 2. This is the square term that we have multiplied by mole per decimeter cube for A. So why I'm directly writing it the concentration of A unit as mole per decimeter cube, because it's nothing but change, and upon adding or subtracting we do not have a change in the unit, so it remains our per decimeter cube, then mole per decimeter cube. Then in down we have this second, that would give us mole per decimeter cube divided by second. Overall we can write this thing, that is decimeter cube per mole per second. So did you get my point? This will get cancelled with this, and this mole decimeter cube will go up. That would give you decimeter per decimeter cube, decimeter cube per mole, and then second will go up, will give us per second. So decimeter cube per mole per second. So this is for one reactant for the first order. Suppose we have two reactants, say A and B. That would give to two A and one A and one B, and both this A and B will have the concentration again. The concentration unit will remain same. There will be no change in this unit section. Okay. So the concentration of A is mole per decimeter cube and B is mole per decimeter cube. Multiplying those two, we will get it as mole per decimeter cube whole to the power 2. Now it is multiplied by again the concentration of A, that is mole per decimeter cube divided by time. That would give us decimeter cube per mole per second. So this is the unit of say K2 in case of second order reaction and two reactants, two different reactants. Now suppose we have third law. Okay, so sorry, third order. So I've not introduced that this. Yeah, I've introduced this order. So rate can be written as minus dA by dt, and again K3 a to the power 3 here. Why? Because it is a third order reaction. So that would left at us with this kind of mess. that is mole per decimeter cube raised to the power 3 multiplied by mole per decimeter cube by second. Okay. Now this decimeter will get a power of 6. T will be cancelled out, we'll get a power of 6 mole per square and then per second. So this is our unit of rate constant. Let us try to generalize this thing. Now we are trying to generalize this thing. So what we have done, we have written that suppose we have a n order reaction. We have a n order reaction. Then what would be the rate law? It would be rate is equals to k a to the power n. This n can should be outside. It is written inside. Sorry for that. Okay. So this n would be outside. Now what would be k equals to rate by a to the power n. Okay, rate by a to the power n. Therefore, what will be the unit of k? If we just try to simplify it, we do it for you. So we have got k is equals to the rate of reaction by time. This rate of rate of reaction by time. Okay, this will be rate of reaction by time, or we can write sorry, it would be not time, it would be time of course, but it will be multiplied by 1 by mole per decimeter cube, mole per decimeter cube. Now since the concentration of reactant is raised to the power n, so I will raise it to the power n. Now it is the rate of reaction with the power of 1. Rate of reaction is mole per liter, okay, mole per liter per second. This is for rate of reaction, and we have this mole n. So since we have multiplied by n, mole n liter minus n. So if we bring this mole here, it would give us mole raised to the power 1 minus n liter raised to the power n minus 1 multiplied by per second. So this is a general form. I have written it here also. Mole 1 minus n liter n minus 1 per second, or here also. Now if you take different type of order, so first we have taken this 0 order. So if you put here 0, n is equals to 0, so what would it give us? So this is our equation. So for n is equals to 0, we will get it as 1 minus 0 L 0 minus 1 per second. That is mole 1 L minus 1 and per second. So this is our thing for 0 order reaction. Suppose we have half order reaction. We take a fractional. So I have told you earlier, order of reaction can be half. So this would be half mole 1 minus 1 by 2 liter 1 by 2 minus 1 per second. That would give us mole half liter minus half and per second. Okay, so is this clear for you? So we can use this general form to derive it for different rate, different order of reaction. So this should be clear. So using this, you can write it for first order also. You will get it as per second 1 minus 1 0, that is mole to the power 0, liter 1 minus 1 0, that is liter to the power 0, and per second. So we got this thing. Now what we have studied today. So basically we have seen the rate law, in which the rate law can be written as rate is equals to minus dr by dt is equals to r to the power x k. So this is the differential form. So this should be remembered. Why the differential form? We have used this differential term. We will get the integral form also, but in the later class. This is the differential form. Okay. So this is a differential form. Then we have seen. We have seen what is order. So this x here is equals to order. If we have two reactants, then we will add all this power and we will get the order of reaction. Then we have seen the unit of rate constant whose formula, general formula is this equation. Okay, so this is clear. So this was for today class. In the next class, we will see a different term, that is molecularity, and we will see what is the difference between order and molecularity. The most important part, that we will see the difference between these two. So with this, I end my lecture here. Thank you for your time.